Hello, my dear friends and students. Now I'm starting with electromagnetic induction, fourth part of the series lecture, in which we plan to do these 7 topics, which is clearly listed in upper part of the screen, out of which I'm starting with self-induction. For this, firstly, I'm to define the phenomenon due to which an EMF is induced in a coil due to varying current through the same coil is called self-induction. The flux through a coil of N turns is directly proportional to the current in the coil. Phi is directly proportional to I, and constant of proportionality would be Li, where L is a proportionality constant known as self-inductance, coefficient of self-induction, measured in Henry. I must specify here, in all these discussions, concerned device is inductor coil, which is small solenoid. Here, few more conceptual points related to self-inductance. Weber, Henry. Unit-wise, the same equation could be written like this. With time, d phi v upon dt is proportional to di by dt. It implies that minus E is proportional to di by dt. It implies that E is equal to minus L di by dt. This is another interpretation. Induced EMF. Another way out to obtain E is equal to minus L di by dt. Interestingly, if we analyze dimensional point of view, from dimensional point of view, volt is equal to Henry ampere per second. Another point, for a coil of N turns, the magnetic flux is linked with each turn. Therefore, the net flux will be N times of the flux associated with a single turn, that is N phi v is proportional to I and phi v is equal to Li. Let's understand theoretically what this phenomenon is by a simple diagram. This is I increasing, then battery is opposing. This virtual EMF is arising in such a way that it should oppose this increasing current. Now, second situation. This time, same current decreasing. Now, EMF induced will appear in such a way that it will try to increase this decreasing current. So that's why this time virtual EMF is in opposite direction with respect to the previous situation. These were the 2 simple situation of self-induction. Definition for self-inductance of a coil is numerically equal to the amount of magnetic flux linked with the coil when unit current flows through the coil. Now I'll underline few keywords. Numerically equal to the amount of magnetic flux linked with the coil when unit current. How? Why? I is 1 ampere and phi is equal to L into 1. It implies that L is phi. Hence this definition. The self-inductance of a coil is said to be 1 Henry when a current change at the rate of through the coil induces an EMF of 1 volt in the coil. And this analysis we have obtained from the formula E is equal to minus L di by dt, right? So now here comes self-inductance of a long solenoid. That means we have to find or derive the expression for L, self-inductance of a long solenoid. Let's consider the diagram first. This is battery EMF here. This is current here. This is length L. Capital N is equal to NL. This is total number of turns. This is number of turns per unit length, and this is length. All the time solenoid behaves as a magnetic dipole. So here also this is cross-sectional area A. L length already we have discussed. Now B, due to this solenoid would be B, that means magnetic field due to solenoid. B is mu naught N I, but we need to convert this small n into capital N. Then flux for each turn. Flux means magnetic flux. So phi B is B dot A, but here that angle between both the vectors is 0. So in general, B into A. B is mu naught N I by L into A. But total flux, it implies that total magnetic flux phi B total equals mu naught Ni by L A into total number of turns, because this whole expression was for single turn. Now total flux will be multiplied, so it would be N extra. But phi total is also equal to Li. Therefore, from 2 and 3, we'll be equating both the expressions. Mu naught Ni by L A N is equal to Li. I will cancel out. Therefore, L is mu naught N square A by L. This is the expression for self-inductance of a long solenoid. But there is one more point in this. Sometimes it is asked in the form of tail question that any rod of permeability constant mu R is inserted in between the solenoid, then self-inductance of the system L dash. This time mu R will be multiplied to the expression mu naught mu R N square A by L. Therefore, hence the topic is over. Then here comes energy stored in an inductor. So energy stored in an inductor. This topic is again very much magnetic counterpart of energy stored in a capacitor. As energy stored inside the capacitor in the form of uniform electric field, same way energy is stored in an inductor in the form of uniform magnetic field, B, Lenz's law, and hence does work for the same. That means in order to do opposition to the battery, some work has to be done inside the inductor coil, and this work done is stored in the form of inductor energy. That means inductor energy is in the form of uniform magnetic field. Considering same diagram of self-induction, this very diagram I was considering theoretically. This work done by the source stores form of magnetic energy in the coil, induced EMF E is equal to minus L di by dt. Now work done in establishing the current in small time interval dt. dw is P dt. P is power, that is equal to minus E I dt, where E is the potential across that inductor coil, minus for E minus L di by dt, and outside this bracket I dt, then dt dt, and minus dw is equal to Li di. It implies that W is L outside 0 to I naught IDI L I square by 2 0 to I naught half L I naught square UB is half L I naught square, and this is energy stored inside the inductor coil. And since L value of L depends upon B also, so that's why it is in the form of uniform magnetic field. Here comes mutual induction. This is topic number 4 in this video of EMI 04. That means 3 topics so far we have already covered. Now mutual induction. As already you can guess by the word mutual. In mutual induction, we would have 2 coils, primary and secondary, and both will be mutually inducing each other and generating induced EMF, thereby induced current in them due to another. So that's why it is defined as some keyword 2 coils, by virtue of which each opposes any change in the strength of current flowing through the other by developing an induced EMF. Now consider, firstly, I would like to draw the diagram of one primary and the other secondary coil. We are to include a cell or battery in primary coil, and because of that primary current, in secondary coil, induced current will be appearing. This is primary galvanometer. Now labeling thing. This has a current plus 1, primary coil C1. This is secondary C2. Secondary में there would be, here it should be I1, here it should be I2. All labeling is done. Consider 2 coils C1 and C2 placed as shown. By varying current I1 in C1, we change the flux. Change in flux phi2 to C2 due to change in I1 induces an EMF in C2. This EMF is known as mutually induced EMF, and the process is known as mutual induction. I'm willing to underline few keywords. Now mathematically, phi2 is proportional to I1. That means flux for second coil will be directly proportional to current in first coil. That means primary. 1-1 notation is being used only for primary here, and 2 second here is secondary coil. It implies that phi2 is equal to MI1, where M is called mutual inductance of the pair of coils. Here C1 is primary, and as you can see, primary is C1 coil and secondary is C2 coil. Now EMF induced in secondary coil, E2 is d5 dt di1 upon dt. Point to be noted where notation 2 is used and where 1 is used. Mutual inductance is maximum when the coils are wound up on the same axis, and it is minimum when the axis of coils are normal to each other. Maximum when the same axis, minimum normal. That means when both the coils are like this, then mutually both the coils will be influencing each other in least manner. But suppose if these two are placed like this, then both of them will be influencing mutually most strongly, I mean. And I had to underline this point again. Capital M is also measured in Henry. I'll be coming on to this defining capital M also. But before that, I'm willing to share one simple diagram exhibiting mutual induction among primary and secondary coils. So here clearly seen how primary coil and secondary coil, both the coils are sharing flux, and Henry already I have talked about. Now defining mutual inductance from the formula, E2 is equal to minus M di1 upon dt. If di1 upon dt is equal to 1, then E2 is minus M. So the mutual inductance of two coils is said to be 1 Henry when a current changes at rate of 1 ampere per second in one coil induces an EMF of 1 volt other coil. This point I am to write, and coefficient of mutual inductance I is 1 ampere, then M is equal to, if I1 is 1 ampere, then M is equal to phi2 is correct. Coefficient of mutual induction of two coils is numerically equal to the amount of magnetic flux linked one coil to unit current neighboring coil. This is also known as mutual inductance. Both are same thing, coefficient of mutual induction or mutual inductance. And last point under this topic of mutual induction, mutual inductance depends upon factors affecting capital M. Number 1, geometry of two coils. Number 2, distance between two coils. And number 3, relative placement, two coils, orientation of the. Now I'm switching over to next topic, mutual inductance of two long solenoids. Here we are given two solenoids S1 and S2, and both are shown in the form of coaxial solenoids. That means both the solenoids axes are common. In first solenoid, current is I1, and in second solenoid S2, current is I2. Here in the given situation, as we can see, L1 is equal to L2 equals L, but A1 is less than A2. It implies that R1 is less than R2. See, this is R1 and R2 is shown like this. But both the solenoid has a length L that is same. Now, flux for first coil, phi1 equals M12 I2. That means flux for first solenoid will depend upon second solenoid's current, that is I2. And also, phi1 is equal to B2 A1 for each turn. And this is very, very important derivation for 12 boards. It implies that this was for each turn, but now total flux, for total flux purpose, total number of turns has to be multiplied, that is N1. But for first solenoid, magnetic field will be second. Because of second magnetic field, since we are into mutual induction, so second solenoid's magnetic field will be causing flux in first solenoid. but number of turns will be खुद का self. So B2 A1 and N1. B2 will be mu naught N2 I2, because already we knew B is mu naught Ni, and also N1 is equal to N1L for A1 pi R1 square N2 L. This is equation 2. Therefore, from 1 and 2, M12 I2 is equal to N2 I2 pi R1 square N2 L, and here we go, I2 and I2 cancel. It implies that M12 is mu naught N1 N2 pi R1 square L. This is equation number 3. Now same process we'll be doing for second solenoid S2 also. Similarly, for S2, phi2 is M21. And let me clarify, M12 was mutual inductance of S1 with respect to S2. Same way, inductance of S2 with respect to S1. Back M21 I1. This is equation number 4. Also, phi2 is B1 A2 N2. Total flux for S2. Again, let us first clarify flux for second coil, second solenoid is due to S1 current, and also flux for second solenoid S2 is due to first solenoid S1's magnetic field, because it is mutual induction. Now I'm to expand again B1 A2 N2. Phi2 equals mu naught N1 I1 pi R2 square here into L. This is equation number 5. Now from 4 and 5 we can write M21 I1 mu naught N1 I1 pi R2 square and 2L I1 cancel. It implies that M21 is mu naught N1 N2 L. That time also I wrote L pi R2 square. Now coming back to our original diagram here. Now empty space between these two solenoids. Here in this region there lies no magnetic field lines. For S2 also, R2 is irrelevant. For second solenoid's flux also, we would be considering R1 only. Although finally we have R2, but we'll be ignoring this R2. That means exchanging R2 for R1. Now what do we mention? Empty space. Both the solenoids has no magnetic field. Therefore, only inner radius is to be considered for second solenoid S2 also. Therefore, M21 is equal to mu naught N1 N2 L pi R1 square. Now this has become equation number 6. Now coming back to equation number 3, as you can see, same expression is obtained. Mu naught N1 N2 pi R1 square L. Mu naught N1 N2 L pi R2 square we have replaced by R1 square. It implies that M12 is equal to M21. From equation 3 and 6, M12 equals M21 equals mu naught N1 N2 L pi r1 square, and that is equal to m. And if we transform this expression into slightly simpler form, therefore m is mu naught for small n1, n1 by L, for small n2, n2 by L, and that is 1L is already there, pi r1 square. L cancel. It implies that m is mu naught n1 n2 A by L, where A is smaller cross-sectional area, which is relevant for the purpose. So both these expressions are useful for numerical purpose. Hence, this heading is also done.